talking about principal series representations, which are representations that are very important in harmonic analysis on semi-simple Lie groups. And I'm going to be talking about a new way to possibly extend this definition to direct limit groups. So first I'll mention what is a direct limit group. So if we start with for instance, an increasing chain of Lie groups, G sub n, where n is an integer, and G sub n is a subgroup of G sub n, if n is less than or equal to m, and then we take the union of all the GNs, we get a new group, and we can give this group the direct limit topology, which is very simple. Subset is open if and only if its intersection with each finite dimensional or each subgroup G sub n is open. So an example of this sort of construction would be if you take the groups SLN. Well, SLN is always a subgroup of SLN plus 1, and one way of embedding SLN as a subgroup of SLN plus 1 is to take when your n by n matrix A and construct an n plus 1 by n plus 1 matrix where you stick A up here in the upper left-hand corner, a 1 down here in the lower right-hand corner, and zeros here and here. Okay, and then you can take the direct limit of these groups, and you get an infinite dimensional group called SL infinity. And you can do this same trick with basically any of the classical linear groups. So there is a group SO infinity, SU infinity, etc., etc. Okay, so why should you be interested in these groups? Well, for one reason is that these are sort of the smallest infinite dimensional Lie groups that you can construct, right? They have countable dimension, and they're sort of built out of finite dimensional things. So they sort of inherit a lot of properties of finite dimensional Lie groups, and they just begin to show the pathologies of infinite dimensional Lie groups. There's sort of this in-between case in some sense. I have this sense that they should somehow be useful in physical applications for modeling systems with infinitely many degrees of freedom. Of course, one problem with any infinite dimensional Lie group is that there's no Haar measure, right? Because Haar measures exist if and only if you have a locally compact group, and infinite dimensional groups are not locally compact, so they can't have Haar measures, they never do. So if you want to you can always consider representations of these groups because they're topological groups, and you can consider unitary representations of any topological group. It's a question you can ask. But the basic questions for harmonic analysis, you sort of can't ask in the same way because you don't have a Haar measure. So you need a correct context for that. So one thing you might hope is that maybe if you could come up with the correct context for harmonic analysis, then maybe you'd get some representations that would be analogous to the representations that show up in harmonic analysis for the corresponding finite dimensional Lie groups. So in the case of semi-simple Lie groups, you'd hope for things like principal series representations. Well, complementary series representations aren't so important for harmonic analysis, but actually they're sort of the impetus behind this particular project I'm going to be reporting on today. Because we were trying to do something called reflection positivity for direct limit groups is how this project got started. And without going into the details, you end up with this connection between discrete series representations of certain groups and complementary series representations of other groups. So we wanted to construct complementary series representations in an infinite dimensional context. And I should mention this is joint work with my former advisor, Gestur Ólafsson, Stéphane Merigon, who has since left mathematics, and Sean Taylor. Let's see here. So let's review let's review the definition of principal series representations in the classical finite dimensional context. We're going to restrict ourselves to just the unitary spherical principal series for this talk. So let's go ahead and start with a non-compact semi-simple linear Lie group without compact factors. And we'll pick a parabolic subgroup. It doesn't have to be a minimal parabolic. In fact, for us today, it'll be the maximal parabolic that's most interesting. Parabolic subgroups always have this decomposition this Langland's decomposition m times a times n, where a here is an abelian group, n is nilpotent, and this group m is chosen in such a way that m times a is the centralizer of a. Now, in the case of the minimal parabolic, m is actually compact, but for any of the other parabolics, it's no longer going to be compact. Okay, so it turns out that G admits everything in G can be written as a product of something in K, something in M, something in A, something in N, and really I should put little labels on M, A, and N because they depend on the parabolic that I choose. And then I can consider the homogeneous space G mod P, which is a flag manifold. And because of this decomposition, you can think of G mod P as it's diffeomorphic to this other homogeneous space where K is acting, where K is the symmetry group, K mod K intersect M, and the diffeomorphism is given by just take anything in G mod P. So here I've written G times P, where G is something in the group G, and then I just send it to K of G, where G, the representative for this element of G mod P, can be written as K of G times M times A times N, and then I just send it to whatever corresponds to K of G over here. Okay, and this of course gives me a way to transfer the action of G on G mod P to an action of G on this space. To define the principal series representation, we're going to be inducing representation of P to a representation of G. To do this, you need to consider sections of certain vector bundles over G mod P. And here we are going to get into the actual measure theory is important. So we need to consider L2 sections. And although G mod P doesn't have a G invariant measure because P is actually not a unimodular group, it does have a K invariant measure because G mod P is just the same thing as this compact homogeneous space as a space where K acts. So it automatically has a K invariant measure, and that measure is quasi-invariant under G. So if you act with G, you get a Jacobian which comes out, and that gives you a radon-Nikodym derivative for this K invariant measure mu, shifted by an element of G. So that gives you this cocycle, this function rho, which is a function of an element of G, which acts on G mod P, and then an element of G mod P. Okay, and in fact you can say exactly what it is in this case. In terms of representation theory data, this rho is actually half the sum of the positive restricted roots which come from the root system associated with this parabolic. Okay, so how do you construct the unitary spherical principal series representations? So I said that this group A was an abelian Lie group, so you consider its Lie algebra, fractor A, and its the complexification of that Lie algebra. And then lambda is something in the dual vector space, so it's a functional on the complexification of A. And then what I'm going to do is define a representation of P by separately considering representations of M, A, and N and putting them together. So in this case, I'm going to use a trivial representation of N. I use this weight on the Lie algebra A to define a representation of this abelian Lie group A. So this lambda gives me a weight on the Lie algebra of A, which then on the exponential map gives me a representation of the group. And then, because I'm interested in the spherical principal series for this talk, among other things that makes things more simple, I'm going to just start with, I'm just going to consider the trivial representation of M. So you put all these together, and this gives you a definition of a one-dimensional representation of this parabolic group M times A times N. And again, all I'm really doing is basically taking this weight on A and exponentiating it. Okay. So then I can take this representation and induce it from the parabolic subgroup up to G. And again, since L2 of G, and essentially what's happening here is because I'm starting with the trivial representation of M, the vector bundle I get is trivial. So I can think of this as a space of functions. And because I'm using a one-dimensional representation of B, they are functions to just the complex numbers. So the space it acts on is L2 of G mod P, which is the same thing as L2 of K mod K intersect M. And it basically, it acts almost like translation, right? You act on a function here almost by translating it. So first of all, what's going on here, this K of G inverse X, is basically saying I act by translation, but if I'm translating by something in G, I need to use the action of G on this space. So that's why I've written K of G inverse X, which is giving me the action of G on this space. Then this here is the Radon-Nikodym derivative, which I put in so that I can actually get unitary representation. So this is basically taking out the effect of that translation has on the measure, right? Because it's only K invariant. So if I were to act by something in K, I would just get F of K inverse X. And then because I'm inducing from this representation of A, that's where this A factor comes in. Okay. And given the formula that you can write down for rho, you can actually rewrite this as in terms of just a power of A, where this is, again, half the sum of the positive roots. Okay. And this is a spherical representation in the sense that it has a K invariant vector, and that's simply because I can consider the constant functions, right? And those are K invariant because K acts just by translation. Okay? Also, it's unitary if I put in lambda purely imaginary, because here, so this takes out the effect that translation has on the measure, and here if I raise this to an imaginary power, well, that's just e to an imaginary number up here, and that's not going to, so I get a unitary representation in that case. Sometimes I can put in not just a purely imaginary number, but a real number, and I'll get something unitary. And when you can do that, you get essentially a complementary series representation. But I won't get into the details because that's still a little bit messy. And in general, when you're doing this principal series representation, almost always you get an irreducible representation of G. Okay, so what we'd like to do is come up with something similar for infinite dimensional groups, for direct limit groups. Of course, the one thing you'd think that might work is, so it's true that if you take a direct limit of irreducible representations, then you wind of groups that fit into a direct system, then the direct limit representation is irreducible, right? So one natural way of constructing irreducible principal series representations, you might think, is, well, let's just take a direct limit of principal series representations. Okay, so there are a couple of problems with that, as we'll see. Or you might say, well, let's just use this induction construction and just induce from a parabolic subgroup up to the big group. Again, one problem with that is that we had to talk about measures, and here the quotient space, the flag manifold, will be infinite dimensional. Okay, so for the moment, we'll just look at the details for the maximal parabolics for SL and R, because that's the example that we're going to see worked out in detail today. So basically, in general, if you take the minimal parabolic subgroup for SL and R, you get the upper triangular matrices. And if you want to consider, so that corresponds to the flag manifold where you have full flags. And if you want to consider other parabolic subgroups, you put things that are upper block diagonal with blocks of different sizes. And then if you consider the biggest blocks, right, the other extreme is if you have just two blocks. So that corresponds to this case where so if you want to consider a maximal parabolic for SL and R, then one way to do that is to fix some number p, some number n greater than or equal to p, and then I'll just, for notational convenience, q is n minus p. Okay, so now SLN is p plus q, and I can consider matrices in SLN as having a 2 by 2 block structure. And in this case, the A subgroup is essentially going to be matrices that are some multiple of the identity on this block and some multiple of the identity in this block. And the trace has to be 0 if I'm looking at the Lie algebra, because it has to be inside the Lie algebra of SLNR. Okay, so I've gone ahead and written q times ip and minus p times iq, because if you take the trace of that, you get 0, and then all constant multiples of that matrix. Okay, and then if you want to include the m part in this, so the Levy factor, you just need the centralizer of that one-dimensional Lie algebra. And if you do that, you get precisely these block diagonal matrices, where here I can have any p by p matrix. Here I can have any q by q matrix, and the only restriction is that the sum of the traces has to be 0. And then the n part is basically the strictly upper triangular in block structure matrices. So here I have 0 in this p by p block, and 0 in this q by q block, 0 in this q by p block, and here I have whatever I want. And you can check that these all commute with each other. Okay, so then I put this all together and I get this maximal parabolic. On the group level, this is what I get. This group turns out to actually be a billion, and this product is just the sum of the, it's just the vector space sum here. Yes, so A here exponentiates to this group where of all the matrices which are multiples of the identity on this block and on this block such that the determinant is 1. I put them all together, I get the parabolic subgroup, maximal parabolic subgroup. Okay, so what you get when you consider the flag manifold in this case is actually a Grassmannian, right? And this is a special case because this is actually a symmetric space, it's a compact symmetric space. So in particular, if I consider just the action of SON on L2 of this space, that's a very simple thing to decompose. I get just the spherical representations. I know exactly what those are. Okay, so this should be a very nice context for constructing these, for constructing an infinite dimensional analog of this context. And notice that I've been labeling everything by a little subscript n, corresponding to, so I'm starting with subgroups of SLN, and that's because I'm going to take direct limits. I can just go ahead and do that. So I'm going to define this parabolic subgroup P infinity as just a direct limit of L infinity times N infinity, where L infinity is just a direct limit of the LNs, just a union of all the LNs. N sub infinity is just a union of all the N sub Ns. It doesn't sound doesn't roll off the tongue very well. Here's a minor difficulty. A sub n is not actually a subgroup of A sub n plus 1. And if you look at the definition here, you'll see why. Because you might say, well, let's just add on ones here like we did before. But the problem is then you no longer get something in this group where you have constant times the identity matrix here and constant times the identity matrix here. Okay. And in fact, this observation is the key to making this whole construction work. Because once you realize this, you say, well, let's just forget about the group A. Let's focus entirely on the Levy factor L, which is the product of M and A. Well, there's no problem here, right? L infinity is just you can think of them as infinite matrices, where I've got this P by P block up here, which is in GLP. I've got something here which is in the direct limit of the GLNs, and then the product of the determinants is 1. Now, GL infinity consists of just matrices which differ from the identity by a finite rank operator, and so the determinant of B is well defined. Okay, and then in infinity is precisely this space. Okay. Okay, so now we can go ahead and define our one-dimensional representation of P infinity that we're going to use for the induction. We can just take the absolute value of the determinant of this P by P part A up here and raise it to some power lambda. Okay? And somehow if we choose a purely imaginary complex number, we expect to get something unitary out of this. So we need to define the induction. The problem is that this doesn't have any quasi-invariant measure. So I've already mentioned that infinite dimensional groups don't have Haar measures, and it shouldn't be a leap from there to conclude that it should be difficult, if not impossible, to get invariant measures on infinite dimensional homogeneous spaces, and that's correct. You can't even get quasi-invariant measures. So it sounds hopeless. So there are a couple of ways around this. One way, a very nice construction. So by the way, I should mention that Joe Wolf has a really nice series of papers where the sort of general classification of parabolic subgroups in the context of direct limit groups and parabolic subalgebras is considered, and then also where a possible analog of principal series representations is constructed, and one way around this is use an invariant mean, okay? Because SO infinity is an amenable group, so maybe you can use an SO infinity invariant mean on this, and then that should give you something like an L2 space. So invariant means are things which are sort of like poor man's measures. They are instead of being elements of the dual of the compactly supported continuous functions, they're elements of the dual of the bounded uniformly continuous functions. The problem is that when they exist, they're not unique. In fact, if a group is amenable, in general, the cardinality of the set of all invariant means is 2 to the order of the group. So it's the non-uniqueness is as bad as it could possibly be, and to prove that it exists, you need the axiom of choice. Now, this is not as bad as it sounds, because oftentimes you can prove that something holds true for all the invariant means. And it turns out to be something analogous to what happens in the classical context of harmonic analysis. But nevertheless, it might be nice to get an actual measure space, where there's an actual group acting on a measure space, and you're actually considering honest-to-goodness L2 functions on some measure space. So it turns out that Doug Pickrell has an old paper from the mid-'80s where just such a construction is done for the complex Grassmannians, but it works for the real Grassmannians just as well, where instead of considering this space, you need to consider a certain extension of this space to something bigger, which does have a measure on it, which is invariant under SO infinity. So it's no longer a homogeneous space. It's something like a homogeneous space which has been thickened out in some sense. Okay, so how is this defined? We start with the Grassmannian of p-planes in Rn. Okay, so this is all p-planes in Rn. So here SLN acts naturally on this space just by, well, you take some subspace, some p-dimensional subspace, and act on it with something in SLN that gives you another p-dimensional subspace. Okay, so you act point by point at every element of the vector subspace. Now, it turns out that we do have a projection from Rn plus 1 to Rn, right? Where we just forget about the last coordinate, okay? So, it turns out you can define a projection from the Grassmannian of p-planes in Rn plus 1, the Grassmannian of p-planes in Rn, by just saying, okay, if I have some p-plane in Rn plus 1, I'll just take that p-plane and I'll project it using this projection. I'll take the image of that plane under this projection, and that will give me a subspace of Rn. Okay, now you should be complaining that won't always give me, a p-dimensional subspace of Rn. But if it does, then I'm golden, right? And And since we really only care about measure spaces, and since the case where that doesn't happen is measure 0, we can just define some default value in this measure 0 subset, and then we have a measurable projection, which is continuous almost everywhere, except for on this sort of bad set, this singular set, right? Okay, so this map is actually SLN equivariant. So in other words, if I act on something up here, by something SLN, not an SLN plus 1, but something SLN that only acts on the first n coordinates, and then project, that's the same thing as if I first project and then act by something in SLN. Because it's not doing anything, SLN doesn't do anything to that last coordinate. Okay, so this is SLN equivariant almost everywhere. Ignoring this set of measure 0 that's problematic, we have an equivariant map. Okay, and then you can consider the projective limit of these measure spaces. Okay, so instead of constructing an inductive limit of spaces, here we have a projective limit, and not of topological spaces because these aren't continuous maps, but as of measure spaces. Okay, each of these spaces has a unique SON invariant probability measure, and because I just told you that these are equivariant maps, it has to project the SON plus 1 invariant probability measure up here to an SON invariant probability measure down here. So if everything is normalized, we have to move from the invariant probability measure up here to the invariant probability measure down here. Okay, so then we have a projective system of invariant measures, and by Kolmogorov's theorem, you can construct the projective limit measure, which is a probability measure, on this big space. Okay, and this is a big space on which the group SO infinity acts. And this measure is going to be invariant under this group SO infinity. And furthermore, the L2 space of this big measure space is just a completion of an inductive limit of the L2 spaces of the finite dimensional spaces. Okay, this bar here stands for Hilbert space completion, and this bar here is indicating that we're constructing the projective, not the inductive limit. Okay, so the important thing is that this can be done in such a way that we not only have a measure here that is SO infinity invariant, because you can already see that in the paper of Pickrell, at least for the complex Grassmannians, but it all works, or the real Grassmannians. The important thing is that the measure here is, because this is like the flag manifold, right? So it needs to not just have a K invariant measure, but a G quasi-invariant measure. In this case, G is SLN. So the measure needs to be quasi-invariant under the action of this big group SL infinity. Now this is trickier because now we're acting with a direct limit of non-compact semi-simple Lie groups. So it's a little bit more of a stretch to ask for it to still be quasi-invariant in the direct limit because it's not even an amenable group. But it turns out that it works out. So one thing is that you notice that that if you consider all the linear maps from Rp to Rn, so in other words, P by n matrices, that gives you a GLN principal bundle over the Grassmannian. Okay, so and the projection is just literally taking the image of the linear map from Rp to Rn, and that gives you a p-dimensional subspace. So these are, I should say, sorry, these are rank P matrices. Sorry, that's a typo. I should have said rank P matrices. Okay, so this map is equivariant under the action of SLN on the left. And then this big space also has an action of GLP on the right. Right? It's a GLP principal bundle. Okay, the projections. There's the projections that I just mentioned on the level of Grassmannians are easy to describe on the level of these matrices. I just lop off the lower rows, right? So in other words, I'm forgetting what this information tells me about the image on the last coordinate. Okay, so this projection is easy to write down. So if I start with Lebesgue measure on this space, I can construct the Gaussian measure. I can construct a Gaussian measure which is actually invariant under SON. Okay? And I can do this at each level. And I can do this in such a way that I have a projective system of measures on MPN. So I do the same trick, and I get in the projective limit of these MPNs another measure which is invariant under SO infinity. Okay. And using Kolmogorov's theorem. And here it's much easier to work out what the to prove the quasi-invariance of SL infinity. I don't think we have time to get into the details. And the reason is because well, it's just a matter of sitting with this explicit formula and writing out the Radon-Nikodym derivative. You know that on each finite dimensional level it's quasi-invariant, because quasi-invariance just means that you have a measure which is locally Lebesgue, and that's certainly the case here. And then what you do is you show that the Radon-Nikodym derivatives are cylindrical functions on this projective system, which means that that you get a measure which is quasi-invariant in the limit. So then you can write down explicitly what it is, but once you have that, then you can then define a representation by taking this Radon-Nikodym derivative, taking the square root of it, and then so if I put a lambda purely imaginary here, I get a unitary representation. Okay, and that is what I'm saying is a candidate for a unitary spherical principal series representation. The point is that because it turns out that you can show that this is actually a direct limit of spherical representations, because the L2 of this projective limit space is a direct limit of L2 spaces at each level, and because the Radon-Nikodym derivative of the action of SL infinity is a cylindrical function, that tells you that this has to be irreducible almost everywhere, because you're taking a direct limit of irreducible representations. It's spherical because I can just consider constant functions on this projective limit of Grassmannians, right? And so if I act with something in K infinity, which in this case, sorry, is SO infinity, then it stays constant. And it's unitary if I choose something in purely imaginary. A similar construction works for the finite rank parabolic subgroups, and it seems like it should work in general for all of those. Okay, so what are we working on right now? This is actually still a work in progress. We're working on explicitly describing the K-types of this representation. In principle, it should just be a direct sum of, because we actually have a symmetric space, a direct limit of symmetric spaces here, in the case of the Grassmannians. It should just be a direct sum of all of the spherical representations for this direct limit of symmetric spaces, which we've already classified in earlier work. So that should be, that's the expectation, but weird things happen, and similar work in another context by Olshansky and Borodin went in a completely different direction, where you wound up with point processes that correspond to log gas distributions, things that had no correspondent, no equivalent. They didn't seem to correspond to anything in classical harmonic analysis. But there's reason to suspect that it should be simpler in this case. Again, the impetus behind this was originally trying to construct a complementary series representation, so we'd like to do that. Can you do something similar for minimal parabolic subgroups? This construction seems to be breaking down, but there may be another way to fix it. And one thing that I'm particularly interested in is if you construct an SL infinity quasi-invariant measure on something like a projective limit of these Riemannian symmetric spaces. Okay, so thank you very much for listening. And happy birthday to Adolfo. I would sing Las Mañanitas, but I don't want to torture everyone before lunch. Yes, and we've We've already considered that, and it's so basically the reason for considering this particular context that I mentioned today was starting from that more general context, exactly, of those symmetric R spaces, and we were looking at the canonical representations and trying to sort of generalize that from the finite dimensional context to the infinite dimensional context. So what you're saying is correct, and it seems like if you start with that context and then look at the direct limit case, it seems like all of this should work out. But again, I don't think we've worked out all the details except for in this particular case. Does that help answer your question?
Any other questions?
You said that to find the K thing that's just work in progress, right? So
yes.
There's nothing known about
in this particular example, so there are other examples of direct limits of symmetric spaces where, so Borodin and Olshansky, for instance, considered the groups U of n. And of course, U of n is a symmetric space, right? It's U of n cross U of n mod diagonal. Okay, and it turns out that these are symmetric spaces with this as the symmetry group. It turns out that there's a way to construct a projection from un plus 1 to un almost everywhere, which is continuous almost everywhere, exactly in the same sense that we just discussed here for the Grassmannians, where it's actually equivariant. This map is equivariant under the action of un cross un on the left and un on the right. Okay, then you put Haar measures on each of these, consider the projective limit, you get something in the projective limit, which is, you get a measure on the projective limit of these, which is invariant under the action of u infinity. And this ended up being a series of 2 or 3 long papers with lots of details by Olshansky and Borodin, where they worked out all the details of the decomposition of that representation. They called it harmonic analysis on the infinite dimensional unitary group because it's in some sense an analog of decomposing the biregular representation of un. And it turns out that it's very difficult. At each level, you know exactly what the representations are, right, by Peter Weil and highest weight theory. And what you essentially need to do is look at the combinatorial data of each representation up here gets sent to a un representation up here, but it's sort of split among different un plus 1 representations, and you sort of need to know what's the inner product, in some sense, among each of the components up here, and then look at asymptotics of this combinatorial data. And you wind up considering, with, there's lots of probability theory, and actually point processes come into play. And this is where this log gas distribution I was mentioning came up. But so this is the only case that I know of in the literature where the details have been worked out. In this case, I can't find it. Somebody once told me that Olshansky and all them know the answer and worked it out, but it's nowhere in the literature. And so, but there's reason to hope that it should be simpler in that case.